We're focused on the inverse problems and very special cases of them. We've handled the one equation, one unknown case. Now let's go to the next simple special case. Here we'll stick with one equation, but greater than one unknown. So the problem data is the A elements, A11 up through A1m, and Y1, and the equation is as follows. What is x? Again, there's three cases. If all of the a's are equal to 0 and y equals 0, then there's clearly an infinite number of solutions. Any value of x is a solution. On the other hand, if all of the a's are equal to 0 and y isn't 0, then there's clearly no solutions. And finally, there's the case when all the a's are not equal to 0. So therefore, at least one of the a's, let me call it A1q, is not equal to 0. Then there are an infinite number of solutions. How? Let's solve for xq by simply rearranging the original equation as this. Notice this requires that A1q is not equal to 0, so we can divide by it. It's clear that you can choose arbitrary values for all the x's except xq, and then solve for the xq, which renders the original equation solved. Moreover, if the original equation is solved, then by rearranging, this is clearly the value that xq will take on in terms of the other x's. Therefore, this does represent all solutions to the problem. Now exchange and have many equations and only one unknown. The problem data are the values of the a's and the value of the y's, and the equations are of this form. Many equations, one unknown. Four cases here. If all of the a's are equal to 0 and all of the y's are equal to 0, then any value for x1 works. If for some k, one of the a's is equal to 0 but the corresponding y is not equal to 0, then clearly there are no solutions, since no value of x1 would work for the kth equation. For the third case, suppose that at least one value of a is not 0. Let's say ak1. That means that the only possible solution, which would render the kth equation solved, is that value of x1. And then it becomes a question, does that solve all the other equations? That question is the ith a times that solution for x1 equal to the ith y? Remember that ak1 is not equal to 0, so move ak1 over to the other side, and we simply end up with this condition. ai1 yk equals ak1 yi for all I. If that's the case, then there exists one and only one solution. The final case has the same setup. At least one entry of A is non-zero, but for some I, this matching condition for the other equations does not hold. Clearly then, there's no solutions. This now gives us a general way to think about these inverse problems. Turns out there are four cases to consider, three of which we've just now addressed. The first three cases are that n and or m equals 1. In that case, we can use the appropriate case that we just derived. The remaining situation is that both n and m are greater than 1. We'll handle this by reducing it to one of three cases. Either an easy infinite solution case, or an easy no solution case, or we can reduce the problem to one fewer equation and one fewer variables, and then use recursion, leading to a base case of either n and or m equal 1, where we use 1, 2, or 3 as previously derived, or one of these easy solution cases for the case when n and m are both greater than 1. Let's see how this goes. One possibility is that all entries of A are equal to 0 and all entries of y are equal to 0. Well, that's an easy infinite solution case. Any value of x works. Alternatively, it might be that all the entries of A are 0, but some of the y's are non-zero. That's an easy no solution case. No value of x works. Finally, there's the case where at least one entry, I'll call it A sub kq, is not equal to 0. The kth equation is of this form, and akq is not equal to 0. Therefore, we can solve for xq in terms of the other x's, simply moving that term to the other side and dividing. I can substitute this expression into all of the remaining equations, leaving one fewer equation and one fewer variable, since xq is no longer a variable. It's solved for using the explicit formula above in terms of the other variables. In this case, there's fewer equations and fewer variables, and then we can use recursion, as described on the previous slide. So the conclusions that we reach at this point, without too much work, is given an inverse problem. The data is all the elements of A and all the elements of Y. There are only three possibilities. There exists no solutions, there exists a unique solution, or there exists an infinite number of solutions, and in fact the infinite number of solutions is of the form one or more of the x's are completely free and the others are given as linear or affine functions of these free variables. The derivation was recursive with elementary base cases and elementary recursion, a nice application of what you learned in the previous few lectures. For square systems where the number of equations equals the number of unknowns, the backslash operator in MATLAB implements something close to this approach that we just derived, returning the unique solution or giving a warning which corresponds to the no solution and or the infinite solution cases. It doesn't directly address those, it just gives a warning. So our next main order of business is to cover this operator, but we need to introduce some new notation for describing linear systems of equations.